Welcome to our module about acoustic porosity tools. In this module, we will learn the functionalities and application of acoustic porosity tools. We will review the logging conditions in which these tools can be used, and we will learn the principle that explains how to go from acoustic signals to porosity values. The primary objective of logging an acoustic porosity tool is to determine formation porosity. Unlike porosity estimates from neutron and density tool, which reflect the total porosity, acoustic porosity tools indicate effective porosity. This is important because effective porosity helps determine if the fluid in the formation can be produced. Another reason why clients request that an acoustic tool to be logged in their wells is to provide the information necessary for time-to-depth compression on seismic surveys. When combined with neutron and density porosity measurements, sonic logs can identify gas-bearing formation and assist in lithology identification. Acoustic logs are also used to determine mechanical properties of the rocks. Talking about the logging conditions, sonic tools are capable of acquiring data in most well conditions, including freshwater-based mud, saltwater-based mud, and oil-based mud. However, they cannot provide accurate data in air-drilled boreholes, since sounds does not travel well through air. Acoustic porosity tools in wireline logging measure how quickly sounds travels through formation rocks. The principle to get porosity values is that if sounds travel fast through the formation, this formation is likely to be solid and has low porosity. But if sound travels relatively slow, then there must be pore space filled with fluids that are slowing down that sound waves. The key measurement here is called delta T, also known as interval transit time or slowness. Delta T represents the time it takes for sound to travel through 1 foot of formation. Let's explore how this sound is generated and measured. The tool consists of one or more transmitters and multiple receivers spaced along the tool's length. The transmitter converts an electrical signal into mechanical energy, causing the transmitter material to rapidly expand and contract. This vibration generates acoustic waves that travels through the borehole fluid into the surrounding rock formation and back to the receivers. Then the receivers detect different types of returning waves, primarily compressional P waves and shear waves, also known as S waves. By precisely measuring the delta T of the compressional waves, we can calculate formation porosity. The relationship is straightforward. As porosity increases, the compressional delta T also increases. Again, remember that in more porous formation, sound waves travel more slowly because they encounter more fluid-filled spaces. These pore spaces slow down the wave's journey, resulting in a higher delta T value. So, a higher delta T indicates more porous formation, while a lower delta T suggests a denser, less porous rock. To summarize, the tool emits acoustic waves, and we calculate the velocity of these waves by knowing the time they were generated and the distance between two or more receivers. There are many types of wave generated, but we are interested in calculated delta T values for critically refracted compressional waves and shear waves because porosity is proportional to the wave's velocity. When talking about acoustic tools, there are a few key concepts that are important to have clear. So let's cover them. Travel time is the time elapsed from the moment the transmitter pulse is generated until an acoustic waves arrive at the receiver. Since this concept depends on the distance transmitter to receiver and will vary on each tool, a way to standardize this is to measure sound speed in terms of delta T. Delta T is the time required for sound to travel through 1 foot interval of formation, usually expressed in microseconds per foot. To compute its value, we consider different vectors representing the way sound travels from transmitter until it reaches at least 2 receivers. Then we divide the distance between receivers as shown in the formula. Moving on this table, on the red column, we can see values associated with delta T values for different types of formation and different types of fluids. And the values of velocity shown in the green column are simply derived from dividing 1 million by delta T value. Next, the transmitter to receiver distance is known as offset. A longer offset makes the acoustic tool capable of determining formation velocities in much larger diameters boreholes than a short space tool. Another advantage of a great offset is that the longer it is, it provides more time separation between the first arrival of critically refracted compressional waves and shear waves at the receiver, which make it easier to detect with a greater degree of accuracy. Now in this image, we see the distance between individual receivers, which is called spacing. Let's think about the fact that once the signal is emitted by the transmitter, it travels in different forms. Some waves are reflected back. Some of them get lost into the formation after being refracted. But the ones used for peak wave computations are those critically refracted, because this path represents the path of minimum travel time between transmitter and receiver. So the first compressional wave to arrive at any receiver is one that has been critically refracted. Moving on the types of waves, remember that P waves are compressional waves, which are the fastest and the first to arrive at any receiver. Well, keep in mind that they have the ability of traveling through liquids as well as solids, those making them useful in determining porosity. Shear waves, also called S waves, are created as the fluid pressure wave impinges upon the borehole wall, but the resulting molecular deformation occurs only within the rock and not the pore fluid. Fluids do not support shear deformation. As molecules of the rock are deformed, shear energy causes them to vibrate in a direction perpendicular to the direction of energy propagation. Shear energy traveling through the formation is re-radiated into the borehole, and the resulting fluid pressure wave is then detected at a receiver. There is another type of wave called stonally, which are surface waves created by the flexing of the interface between the borehole fluid and formation fluid with repetitive transmitter pulses. Each transmitter pulse causes a pressure increase on all sides of the tool, which results in minute displacement of the borehole interface. Immediately following a transmitter pulse, there is a sudden decrease in pressure, and in the fluid interface rebounds. This flexing of the fluid interface propagates up and down the borehole as stonely waves. At this point, we will get into more details on the wave generator process. Some acoustic tools use a monopole transmitter with the purpose of generating critically refracted P wave and S wave for delta T measurements, and from there, porosity calculations. Monopole transmitters are capable of generating stonely waves, whose frequency analysis is used for permeability profiling, but monopole transmitters fail to generate critically refracted shear waves in slowed formations. This is why dipole transmitters are used to measure shear velocity in rocks where monopoles can't. When reading specifications about porosity tools, you will see some of them have a cross-dipole transmitter. That means two dipole transmitters positioned at 90 degrees that, when combined with directional and borehole geometry data, can be used to investigate anisotropy. And what is anisotropy? It's the variation of some physical property with respect to direction at a single point in the formation. We are interested in anisotropy because it can help with the identification and orientation of natural fractures. Also, it serves to determine ideal borehole trajectory in future wells, and many other applications like oriented perforating for sand control and enhanced frac design. We've learned that dipole transmitters create a directional pulse. This results in the creation of flexural waves that travels along the borehole wall. At a low frequency, these waves move at the same speed as the formation's shear velocity, which is key information we want to seek. flexural waves occurred in all formations, even those where monopole transmitter cannot generate critically refracted shear waves. As the flexural waves moves along the borehole wall, they cause pressure changes that are detected by the receiver. Now let's discuss how critical centralization is on any acoustic or sonic log. This image shows the component of the wave sound and the way it travels. If the tool is centered, we could assume that the components A, C, and E are equal, and the calculation of delta T will be as shown in the formula. But whenever there are irregularities in the borehole, may be caused by washout, as shown in the image, the calculation of delta T values and therefore porosity will be affected. Here we can see that the components are not the same, so the calculation won't be accurate whenever in presence of washouts. A similar scenario occurs if the tool is tilted. A common solution for this is to use two transmitters, one on the top of the tool and one at the bottom. Utilizing vertically aligned transmitter-receiver pairs allows for delta T measurements that account for both tool tilt and the presence of washouts. That brings us to the end of our module on acoustic porosity tools. Let's quickly recap the main points we've covered today. We explored the functionalities and applications of acoustic porosity tools, understanding how they measure effective porosity by analyzing the travel time of sound waves through the rock's formation. We discussed the significance of delta T values, the type of waves involved, and the conditions under which these measurements are taken. We also reviewed the importance of tool centralization and how to compensate for tool tilt and borehole irregularities to ensure accurate measurements. Understanding these principles will help us make informed decisions in the field. I hope you enjoyed this lesson. Thank you so much.